Welcome back to our course on mastering numerical method for partial differential equation with MATLAB. In the previous lecture, we presented a few examples using MATLAB Solver. In this lecture, we will discuss solving a single partial differential equation with the given initial and boundary conditions using the PDE PE solver. This lecture will enhance your understanding of PDE and assist you in working with the systems of partial differential equation. So let's start the lecture. Here we are going to solve the single partial differential equation with the MATLAB solver PDEPE. We are considering here the partial differential equation which is given here pi square del u upon del t is equal to del 2u upon del x square. The equation is defined over the interval 0 less than and equal to x less than or equal to 1 and for time t is greater than and equal to 0. With the initial condition we are given here is ux0 is equal to sine pi x. So when t is 0 we have this value. X equal to 0 and x equal to 1, this corresponding to these 2 points. One is for left boundary and other is for right boundary. Left boundary we have is u0t is equal to 0 when x is equal to 0, and when we have x is equal to 1, in that case we are given here is pi exponential minus t plus del u upon del x 1t is equal to 0. So for this partial differential equation with the initial and boundary condition, we need to employ PDEPE solver to find out the solution of this problem and to visualize the result. So first we need to understand the standard form that PDEPE expect, and we need to convert the given partial differential equation into this formula. Okay, so here you can see C, which is function of x t u del u upon del x, del u upon del t, x raised to power minus m, del upon del x of x raised to power m, f, which is function of x t u del u upon del x, and plus s is function of x t u del u upon del x. Here we need to carefully note that C, then we have f, then we have s. All these three are functions of same argument x t u del u upon del x, and also these are known as coefficient of partial differential equation. We need to rewrite our partial differential equation to employ PDEPE solver to convert in this format. Okay, and we rewrite our given partial differential equation which is pi square del u upon del t is equal to x raised to power 0 del upon del x, x raised to power 0 del u upon del x plus 0. So when we compare these two equation number 2 and equation number 3, we can observe that C is equal to pi square and the value of m we have is 0. F is equal to, this is the value of f, and f will be equal to del u upon del x, and the value of s is 0. So these are the values of these coefficient of given partial differential equation. And here also we have again rewrite the same. The value of m is 0, the value of c is pi square, that of f we have is del u upon del x, and s is equal to 0. After that we need a MATLAB code to implement it to find out the solution of these given partial differential equation and with the initial and boundary conditions. So first we need the signature for partial differential equation, and as just now we discussed that these are the input argument for the given differential equation, which are the coefficient of PDE, and all these completely depend upon x t u du upon dx. So these are the input argument, these are input argument, and these are output argument. And PDEx1, PDE, this is just the name of the file which we will save with this name. Okay, if you want to change, you can do. X is the independent spatial variable, t is the independent time variable, u is the dependent variable being differentiated with respect to x and t. Du dx is the partial derivative del u upon del x. The output CFS correspond to the coefficient in the partial differential equation form expected by PDEPE. The coefficient are coded in terms of the input variable x, tu, du, dx. So this is all about the signature for partial differential equation, and following the same we will write the MATLAB code. And here you can see we have the MATLAB code which will be used for the PDE. Okay, this is the signature as we discussed just now. CFS is equal to PDE x1 PDE xtu du dx, and in the MATLAB we start from function. Okay, and these are the corresponding values of the output functions. Okay, our output argument c is equal to pi square, f is equal to du dx, s is equal to 0, and after that we need to enter the function. Then after we need to set the initial condition. We are given when t is 0, u x0 is equal to sine pi x. Okay, and this expression can be written as u0. So u0 is equal to sine pi x. So for this initial condition we need to write here MATLAB code as a user defined function, and this is the signature for the same. u0 is equal to PDEx1 IC, which is used for the initial condition, and there is only one argument which is x, and in the MATLAB we start from function, and this is the initial condition. u0 is equal to sine pi product x, and then we need to enter the function here, and thereafter need to save the file in MATLAB. This is the for the boundary condition for the post on the interval 0 less than and equal to x less than and equal to b. The boundary condition applied for all t and either x is equal to a and x is equal to b. The standard form for the boundary condition expected by the solver is pxtu plus qxt f xtu del u upon del x is equal to 0. So every boundary condition we need to compare with this one, which is the expected for PDE solver. Okay, so when x equal to 0, for x equal to 0 we have u0t is equal to 0. This is the left boundary condition, and can be easily converted to in this form, which is required for PDE solver. We can rewrite u plus 0 del u upon del x is equal to 0. When we compare these two equations, pxt u is equal to u, and when we have the value of x is 0, it is u. So this is the first condition, and we have pl, and qxt is equal to 0, and the value of x is 0, so that's why q0t is equal to 0. This is ql. Okay, now when we have x is equal to 1, for x equal to 1, the given equation, which is this boundary condition, pi exponential minus t plus del u upon del t, 1t is equal to 0, can be rewrite as in this form: pi exponential minus t plus 1 del u upon del x, 1t is equal to 0. Okay, so we need to compare this expression with the standard form. Okay, so when we will compare, pxt is equal to exponential pi exponential minus t, okay, for x equal to 1, and qxt will be equal to 1. Okay, qxt will be equal to 1 for x equal to 1. So this become q1t is equal to 1, and that of p we have is p1tu is equal to pi exponential minus t. This is pr, and this is the value of qr. These are the symbols which we use for the MATLAB syntax. Now here the boundary function should be used for the function signature. We have is here at this place pl, ql, pr, qr. These are the input argument, and XL, UL, XR, URT. These are the input argument, and PDEX1BC. BC is used for boundary condition. PDE is the boundary partial differential equation, example 1. Okay, so this is the name of the function which we will save in the MATLAB. So what are XL and UL? These are input correspond to U and X for the left boundary. XR and UR correspond to U and X for the right boundary. T is independent time variable. The output argument PL, QL correspond to PXTU, QXT for X equal to 0. And the output PR, QR correspond to PXTU, QXT for the right boundary, X equal to 1 for the this problem. Okay, so these are the argument and which are used for boundary condition to write the MATLAB code for the comparison, and every symbol which we are using to write the MATLAB code must be very clear, only then you can write your own code. So here we have the MATLAB code syntax, which is, this is the signature you can find here, PL, QL, PR, QR is equal to PDEX1BC, XL, UL, XR, UR, and T. And in the MATLAB we start from this place by using function. And these are the values of PL, QL, PR, QR, just we discussed in the previous slide, though these are the same, and we need to enter the function. Okay, and save the file with the same name as we put at this place. So you need not change the name of the each file, the name of the script file which you are saving in your MATLAB or in the current directory. All the name which we put at this place must be same, so that when we prepare for the script file of the outputs for the numerical result, we can easily call these functions. Here we need to set up the spatial and time domain. X is equal to line space 0, 1, 2, 0. So 0 and 1, this is the interval, and we divide this interval from 0 to 1 up to 20 grid point. And similarly, we have the line space 0, 2 for time, and grid point we have is 5. Okay. Then after we need to call the function PDEPE at this place, and for this problem we have m equal to 0. Since the given equation is in the Cartesian form, that's why we have m equal to 0. If we are given the problem in cylindrical form, and in that case you will choose m equal to 1. And if the given partial differential equation is in the form of spherical coordinate system, in that case you will choose m equal to 2. So here we need to choose m equal to 0, and we call at the place PDEPE solver, and these are the respective input argument in this order, and always you have to use in this way. Don't interchange all these values, otherwise your PDEPE solver will not work. So here first we have the input argument m, then we have the given partial differential equation, and this will handle the code which we write for the partial differential equation, and this will handle the initial condition, and this will handle the boundary condition, x input argument and t argument. Okay, PDEP return the solution in 3D array solution, and where solution ijk approximate the kth component of the solution uk evaluated at ti and xj. I and j are the just index for t and x respectively. The size of the solution is length t by length x by length u0. Since u0 specifies the initial condition for each solution component, for this problem u is only one component, so solution is 5 by 20 matrix, but in general we can extract the kth solution component with the command u is equal to solution : k, but here we have k equal to 1. Now after that we need to plot the solution. Okay, so first we are plotting the numerical solution. Here is surf x, t and 1. Title we are put at the place heat equation solution, and x label is distance x, y label we have is time t, z label we have is temperature u. Okay, this example set up and solve the heat equation with an initial sign wave distribution and Dirichlet boundary conditions at both ends. The solution is then plotted to visualize how the temperature distribution evolves over time. Here is the analytical solution by employing and simplifying the given partial differential equation by using any method. We have this analytical solution, and when we have the analytical solution, we need to plot this also for the comparison purpose. Okay, so here these are the statement for the visualization of this analytical solution. So here we are using surf x, t. The input value of x and t will be same as for the numerical solution, and this is the solution which is analytical, and the same value we are using here. Title, you can put a true solution plotted with the 20 mesh point, x label, y label, and you can use also z label here. Okay, then after we need to compare these solutions, numerical as well as analytical solution, both at t, at tf. This is the final value of the time, and for example we are taking here tf is equal to 2. The plot function we are using for the comparison, u xu comma xu and comma colon. This is for the numerical solution, and marker is used for the numerical solution x. Then we have this is the analytical solution. Okay, so these two are two solutions. One is numerical and other is analytical for the same argument. A title we have a solution at tf equal to 2, and legend we have numerical solution and analytical solution. Then we have the x label and y label. So this is the complete procedure to write the MATLAB code and save the three files. One is partial differential equation, second is the initial condition, third is the boundary conditions. So these files must be saved in your current directory, and then after you can prepare the script file to plot the graph. Now jump to the MATLAB for the visualization of these result. This is my MATLAB window, and very first we have PDEx1 PDE function, which is partial differential equation as we discussed in the presentation. X, t, u, du, dx. These are the input argument. CFS. These are coefficient of the functions, and output functions, output argument. Okay, and the corresponding the values of CFS as we discussed in the presentation are here. C is equal to pi square, f is equal to du dx, s is equal to 0, and this is the initial condition function PDEx1 IC, and there is only one input argument. U0 is the output argument, and U0 is equal to sine pi product x. Third one we have is the boundary conditions. Okay, PL, QL, PR, QR. These are the signatures for the boundary condition, and also these are output argument. These are input argument for this signature. The values of PL is equal to UL, that of QL is 0, PR is equal to pi product exponential minus t, QR is equal to 1. So these three functions must be saved in your current directory. Then after we will use some sequence of statement to visualize the numerical solution. We will start from CLC, clear and close. X is equal to line space 0, 1, comma 20, and here t is equal to we have is line space 0 to 2. Okay, so maximum time we have is 20, and m is equal to 0. As you know that when we have the given equation in the Cartesian form, in that case we will use m equal to 0. If the equation is in the cylindrical form, in that case you will have m equal to 1. If the given equations are in the form of spherical, in that case you will use m equal to 2. Here we have Cartesian form, that's why we are choosing here m equal to 0. So all these are the input we required for the visualization of the result. Here we will call the function PDEPE. This is the MATLAB solver. Okay, and these are the respective input arguments for this PDEPE solver. m, the value of m is 0, and this is the first given .m file which is used for partial differential equation. This will handle the initial condition, this will handle the boundary conditions, and after solving this partial differential equation, the values will be stored at this place. U is equal to solution : 1. And to visualize these results, we are for the numerical solution, we have the surface XTU. This will plot the graph, okay, and then this is sequence of statement: title, numerical solution computed with the 20 mesh point. X label we have is distance, Y label we have is time t, and if you want to use Z label, you can use also. Z label will be solution. Okay, this is U X comma T. Okay, and box on, box T, box on and grid on. Okay, then after we have the plot for analytical solution, and this will be the figure 2. These are the inputs, so we not required to write separate code, just we have this function is defined here, which is the analytical solution. X and T are the inputs. Then we have the title, X label, Y label, and you can put here Z label also for this plot. Okay, and at the end we have the comparison, the result. Figure 3, plot X, U, and okay, title, legend. Note this very carefully. This is the numerical solution and this is the analytical solution. Both will be compared in the single graph. Title is solution at t equal to 2, legend, X label, Y label, grid on, box on. So everything which we required for the visualization of the results, we have put all the values in the same one specific sequence, and when we will execute this script file, this will plot 3 different graphs. So you can, the MATLAB is busy, it will take few seconds to plot the graph, and here, yes, we have 3 graphs. You can see this is the first graph which is based on numerical solution, and this is the second graph which is analytical solution. This is the analytical solution in the second figure, and this is the third one which is comparison of the 2 solutions, and you can observe that there is no difference of the solutions, and 0 difference is there. Okay, both are absolutely same, numerical and analytical solutions. So this is all about the MATLAB code, how you can write and how you can plot for this from one when we are given one partial differential equation. In conclusion, during this lecture, we explored the PDEPE MATLAB Solver, discussing its syntax for defining partial differential equations, initial conditions, and boundary conditions. We then demonstrated how to set up the spatial and temporal domain for numerical solutions, utilize the PDEPE solver, and visualize the results. Thank you for attending the entire lecture. In the next lecture, we will delve into using PDEPE for solving systems of partial differential equations. Please stay connected and look forward to our upcoming sessions.